This is STA 381, Chapter 2, Section 2. Okay, welcome back everyone. We're in Chapter 2, so we've kind of set the stage about this idea of randomness and events, and so we did some rules about addition rules and unions and intersections and complements last time. So now we're going to go on and talk about some counting rules. So, counting techniques. There are three special ways to look at counting techniques, and by counting I'm talking about different ways of events occurring. So we may be looking at flipping a coin 3 times and looking at the possible combinations there. We may have 10 people and we want to see how many people that we could select randomly in a group of 3 different, how many groups of 3 would there be? So we're looking at different ways of ordering different types of events. Okay, and these counting rules are going to be used to help us get to those answers. So first of all, we have the multiplication rule, we have the permutation rule, and we have the combination rule. And each one has its own place, so you have to really spend a little bit of time getting to know which one you use in which instance. So it's really helpful to go back over the video or go back to the text. There's lots of examples, by the way, in the text. There are video examples in the text. There are video problems, so problems from the section that are worked out via video. There are also interactive problems within the text and outside of the text that you can go through and work examples. So I highly recommend that you take advantage of those. Okay. So first of all, the multiplication rule. Multiplication rule says, let an operation consist of k steps, and then there are going to be n1 ways to complete step 1, n2 ways of completing step 2, all the way up to nk ways of completing step k. Then the total number of ways to perform the k steps is just going to be n1 times n2 all the way up to times nk. So for an example of this, we're going to go over here to the slide. How many different license plates with 6 number-letter combinations are possible if the first 3 must be letters and the last 3 must be numbers, but there are no other restrictions? Meaning that 00, AAA 000 is an example, but in most cases that wouldn't be, but it is here. Okay, so if we want to figure this out, then we're really going to use the multiplication rule to do it. Because if we have a license plate that has 6 positions on it, and the first 3 must be letters, and the second 3 must be numbers. And we can repeat, we don't have any other restrictions, so then all we do is say, well, there's 26 possibilities here, and here, and here, for the letters, and then for the numbers 10 and 10 and 10. So we just multiply all of those numbers together and we end up with 17,576,000 different possibilities for license plates. So if you're in a state that, like Kentucky, that has 3 letters and 3 numbers, then that would be the number of different license plates that you could possibly have. But we know that there's some restrictions, but there's still going to be an awful lot. All right, so let's go back and talk a little bit more. Let's see, we have permutation rule. So the permutation rule, that's our second one of our rules. The permutation is just a unique sequence of distinct items. And so if we have a sample space S, which consists of only the outcomes A, B, and C, then there are 6 permutations of those 3 letters, and we can see those 6 permutations below. So notice that we're looking at 6 different orderings, so the order actually matters, especially in this case. The number of permutations for a set of n items would just be n factorial, and to remind you, if you've forgotten what factorial is, n factorial is just n times n minus 1 times n minus 2, successively down to 1. So 7 factorial, as you can see right there, ends up being 5,040 You can look in Excel and see, you can use the fact function in Excel if you want. We will be using other software in this class, but that's a quick way to do it if you have Excel right in front of you. By definition, 0 factorial is 1, and the thing that you need to think about is that order matters. So the ordering of those items matters. Now, if you want to take a subset of that, then we'll get into a little bit more complex formula for permutations in a second. Now, if we want to, if we want to look at permutations in terms of subsets for a sequence of R items from a set of N items, so R is obviously going to be less than N, we're looking at the permutation, that PNR is the permutation of N things taken R at a time. And that is just going to be N times N minus 1, still the factorial, N minus 2, all the way down to N minus R plus 1. So that can get a little bit laborious if you are, especially if N is fairly large. And so an easy way to write it is just N factorial over N minus R factorial. And you can use your calculator to find that. There's a factorial function on your calculator. There's also within Excel, within RStudio, there's lots of different places that you can determine that without actually having to do it by hand. Just a quick example from the text is example 2.6, and that's a printed circuit board. So we see a printed circuit board has from 8 different locations in which a component can be placed. If 4 different components are to be placed on the board, how many designs are possible? So we start off with 8. We only want a subset of size 4. So as you can see, the formulas used at the bottom of the slide. 8 factorial over 8 minus 4 factorial, which is 1,680. So even with relatively small numbers, there are quite a few different orderings to choosing 4 things from 8. Now, if we want to do permutations where you have similar items, and so you are not able to distinguish necessarily, or you don't really care to distinguish the items into distinct items, you're just going to see maybe have K different items, but you don't really care within those K what they look like. So let's say we have N, which is made up of N1, N2, plus all the way up to N sub R, and that's the number of items in which N1, N2, all the way up to N sub R are identical. And so in this case, permutation formula becomes N factorial, which is the overall N, divided by N1 factorial times N2 factorial, all the way up to N sub R factorial. So we're going to take a quick look at this example a little bit more closely on the slide. So if there are 7 women and 5 men who need to be randomly ordered for a personal training session, then what can we do? We can, so we have 12 people total, so that's our N, and then we have 7 women and 5 men. So we have 12 factorial over 7 factorial times 5 factorial. And you could do this out by hand if you wanted to. I'll just go ahead and do this do it quickly. So I wrote it all out so we could easily see that we could cancel that set of values. We have the 5 and the 2. We have the 4. And then the 3. And then we multiply that out. So we end up with 12 times 11 times 3 times 2. Okay, so that, when you multiply that out, is 792. Okay, so let's go back and talk a little bit more. We have, as you can see, there's just a lot of rules here. So now we're going to go on to the third case, which is combinations. So the combination rule. Combination is just a selection of R items from a set of N where order does not matter. So if you remember a minute ago, we were talking about permutations where order matters. So ABC is distinct from BCA. But with combinations, those two are not distinct. They're the same. So we want to account for that and basically divide out all of those possibilities that are actually identical to each other because order doesn't matter anymore. So in this case, if we have our sample space is ABC, N is equal to 3. If R is equal to 3, there's only one combination, ABC, because ABC, BCA, CAB, those are all the same. If R is equal to 2, our subset is of size 2, then there's actually 3 combinations because we're only interested in subsets of size 2. So AB, AC, and BC, because we don't care about BA, CA, or CB. Those are the same. And so if the number of permutations, it's not an if, the number of permutations will be greater than or equal to the number of combinations. And since the order doesn't matter, as I said, we're dividing the number of permutations by R factorial, where R factorial is the number of arrangements of those R elements. So in the case of what we were just doing before, we're dividing by 2 factorial because we want to get rid of the as I said, we want to get rid of the ones that are the same in our book. And so one way to think about it is called sampling without replacement. That's one way to think about. If you sample something, you don't replace it back. We use the combination formula when we sample without replacement. And our combination formula is very similar to our permutation formula that we saw a couple slides ago. And so we're looking at NCR, which you again can find within your calculator if you have like a TI 83 or 84, etc. calculator. Another way that it shows up symbolically is that N choose R that you see in the middle. And the formula for that is N factorial over R factorial times N minus R factorial. And again, it is different than permutation. So you really need to, when you're looking at these problems, you really need to be careful to distinguish between order mattering and order not mattering. All right, so looking at this example here, we have a bin of 50 parts and it contains 3 defectives and 47 non-defectives. So just as a simple example, how many ways are there for selecting 2 from the 3? Well, this is very similar to what we just saw a minute ago. So we're looking at N choose R, so 3 choose 2, so 3 factorial over 2 factorial times 1 factorial. And so there are just 3 different ways in that case. Again, it becomes pretty laborious to do it by hand. You can, but as you can see, as N and R increase, it becomes a little bit tedious. So again, you can use your calculator, you can use Excel, you can use RStudio, you can use just about any applet out there on the internet. There's lots of ways to do this very quickly without having to crunch the numbers out by hand. Now we'll again remind you that there are examples of problems in Wiley Plus, so please make use of those. I know there's specifically a problem about combinations in there, so if you need some more practice, I would go over to Wiley Plus, look at some of those video solutions and video examples. And that is the conclusion of this lecture.